Hi, welcome to this video in which we'll talk about the thickness of finite conductivity metals in Altair's Feko tool. My name is Zaina, I'm a product engineer at Altair, and I'll try to help you get a better understanding of this topic throughout the video. The question we'll try to answer is the following. How is the finite conductivity of metals accounted for within the method of moments solver in Feko? Let's start with a couple of statements that will help us set the context of the problematic. So practically, metals used in antennas and their surroundings are not perfect electric conductors. And this means, in order for us to accurately design an antenna, ohmic loss effects should be accounted for in the model. We'll start with the simple case of a pack metal. In pack metals, conductivity is considered to be infinite. And this means that there is basically no field penetration within the metal. Thus, the thickness is assumed to be infinitely thin. Now, this case means that there is no skin effect in PEC metal antennas. What happens when the conductivity is not infinite? So when our metal is not a perfect electric conductor. This causes part of the field to penetrate the metal, and we call this skin effect penetration. Now, the method of moment model accounts for this finite conductivity or skin depth by computing an equivalent surface impedance. And in most cases, metal antennas have a finite thickness and conductivity. For MOM computations, the thickness applied to metallic or dielectric faces, as we see here when you try to apply a metal to a specific face in the model, is not a physical thickness. So actually, the thickness we set over here for a given metallic surface is only used to determine surface impedance of that face. What does the skin depth practically represent? It represents the depth underneath the surface of the metal at which the current densities decrease to about 1/3 of their value at that surface. Here you can see the formula, which allows you to compute the value of the skin depth. And we can see that its value depends on the properties of the conductor, and in general, it depends on its size, its resistivity, its magnetic permeability, as well as the frequency of the signal. A last piece of theory here to show you how the thickness you define when assigning a metal to a face is used to compute the surface impedance of that metal for MOM computations. Here you can see the exact expression for the skin effect under condition of good conductors. This is to show where the thickness you input is used in the computations to extract or compute the surface impedance used later on in the MOM computations. I won't go into further details about the expressions that can be used, but you can find more details related to the different formulations in the user guide in the section describing the SK card. Let's run some examples now in which we will model the finite conductivity of a sphere. It's going to be a simple example where we will try to set a metal to the sphere with a specific thickness and to solve with both the method of moments and then run again for the finite elements method and to compare the results. So with this example, we end our video. I hope it was helpful and thank you for watching.